Hello everybody. Last class we have discussed about how to find the motor rating in case of continuous operation or continuous duty operation. Today we will discuss a process to find motor rating in case of fluctuating and intermittent load. In case of fluctuating and intermittent load, the load is variable. In such cases, equivalent or approximation method is used to find the motor rating. Let's take this example. I1, I2, I3, I4, In, etc. are the current drawn by the load in duration T1, T2, T3 and Tn. For n number of loads, or you can say n number of load current drawn by the source, this equivalent expression 11 we can write. Pc is the constant loss across the system which is independent of load. I equivalent is the equivalent current drawn by different loads. Then individual load losses, we can take average of that to equate this expression. So Pc plus I1 is equivalent to R into T1 plus Pc plus I2 is equivalent to R into T1. Like this, we can take average of these losses and equate with Pc plus I equivalent is equivalent to R. Finally, we are getting I equivalent is equal to I1 is equivalent to T1 plus I2 is equivalent to T2 plus In is equivalent to Tn divided by root under T1 plus T2 plus Tn. And this can be, we can write equal to square root of 0 to Ti square dt by t, assuming that smooth current is drawn from the source. So by integration also we can find the equivalent current. Once I equivalent is obtained, then we can decide the motor rating. Next, commercially available motor rating we have to select for that operation. Now, in case of DC machine, if the motor is decided, that means motor rating is finalized, then we can still allow more amount of current from the machine. The reason behind it is that if suppose we are going to use that machine for short duration of time, or you can say short term duty operation, that means for some duration machine is on and enough time is allowed to pull the machine, then higher current can be allowed to the machine. Generally 2 to 3.5 times the rated current or I equivalent is allowed across the DC machine. Similar cases applicable in case of induction and synchronous. But here it should be noted that load torque should not be more than the breakdown torque of the machine. In case of induction machine, the ratio of breakdown to rated torque varies generally from 1.65 to 3, and for synchronous machine it is 2 to 3.5. At the same time, it is also to be noted that if load, you can say ripple across the load is too much, that means peak to peak difference is more. That means for some duration of time load is very high, then load is reduced, then this approximate method is not suitable for that. In that case, we have to use load equalization by mounting flywheel across the shaft of the machine to generate extra torque across the machine or to support the driving torque of the machine. So flywheel will supply the stored energy to support the developed torque to cope up with the load torque. Now, to find equivalent torque or equivalent power in case of fluctuating and intermittent load, similar approach is used. We can take one example here, that in case of DC separately excited motor, we know that current is directly proportional to torque. Then torque equivalent can be written as square root of T1 square into T1 plus T2 square into T2 plus Tn square into Tn divided by summation of the durations. Now, in case of fixed speed drive, fixed speed drive means speed is constant. If speed is constant, then we can say power is directly proportional to torque, because power is equal to torque into speed. So equivalent power also we can find likewise. Till now we have discussed different classes of motor duty. Now suppose a case is there that we have selected a motor for continuous duty operation. Now the same motor is used for short time duty operation. Then what will happen to the machine? Obviously the temperature rise across the machine will not be too much. So we can say our motor is underutilized. Then the same motor which we have selected for continuous duty operation, now we are using for short time duty operation. Here we can overload this, or more amount of current we can allow across the machine. Now how much overloading should be there, based on that we will discuss now. First is that motor operation is considerably less than the heating time constant. That means steady state temperature is not achieved by the machine in short term duty operation. Now the motor rating is PR, that means continuous duty power is PR, and it is applied for short term duty ratio. Obviously it will be underutilized, and the maximum permissible temperature is theta permissible, theta PER. Now let's overload the motor by a factor k. K is greater than 1. Now the load is k into PR. Now the k PR is for duration TR. You can see the graph A and graph B. So graph A is overloaded by a factor k and B is for PR rating. B is operated. Both the operations are short-term duty operation, and from the graph it is clearly understood that B is not attaining its theta permissible value, but A will attain. That means by overloading we can use our motor efficiently. So with KPR the time duration is TR. Then by writing the first order differential equation we can write the expression 15 as theta permissible is equal to theta SS into 1 minus e to the power minus TR by tau. Here tau is the heating time constant of the machine. Theta SS is the steady state temperature rise when motor delivers a power KPR continuously. At the same time, theta permissible, theta PER is also the steady state temperature when motor operates with power PR on continuous basis. Let the motor losses for power PR and K times PR be P1R and P1S. Then from equation number 15 we can write theta SS divided by theta permissible is equal to P1S by P1R is equal to 1 by 1 minus e to the power minus TR by tau. Because theta SS is directly proportional to the loss across the system, heat developed across the machine. Now let's assume P1R is equal to PC plus PCU. P1R total loss across the machine for load PR. It is equal to constant loss plus load losses. So you can say variable copper loss. PC plus PCU is equal to PCU into alpha plus 1. Here alpha is a factor and is equal to PC by PCU. Now let's assume P1S is equal to PC plus K square into PCU. K square is because as load is increased by K times, so current will also increase by K times. That's why this copper loss will also increase by K square times. So PC plus K square into PCU. Then P1S is equal to PCU alpha plus K square. Now putting this equation 18 and 17 in equation number 16, we will get the value of this overloading factor K, and K is equal to the square root of 1 plus alpha divided by 1 minus e to the minus TR by tau minus alpha. So knowing these values alpha, TR, tau, we can easily find how much will be our overloading factor. In case if we are using a machine initially developed for continuous duty operation and now we are using for short time duty operation with on period TR. Today we have discussed about how to find motor rating in case of continuous duty, in case of fluctuating and intermittent load. At the same time we have discussed about if a machine is developed for continuous duty and if it is used for short time duty, then how much will be the loading factor. Thank you.